Welcome to the Introduction to Vblock System Virtualization section of the Vblock Foundations course. Recall that Vblock systems are composed of compute, network, storage, virtualization, and management technologies. In the previous section of this training, you learned about the compute, storage, and network. Now you'll learn about the basics of Vblock system virtualization technology. The objectives for this section are listed on this page. Upon completion of this training, you'll be able to define and explain the benefits of virtualization in an IT environment. Describe each of the following: compute virtualization, storage virtualization, and network virtualization. You will also be able to identify and describe the purpose of each of the components of the Vblock system virtualization technology. In this section, you'll learn about the basics of virtualization, and here we'll spend significant time discussing compute virtualization.
As an IT concept, virtualization is a growing practice used by data centers to source, provision, and manage IT as a service. Virtualization can be a confusing concept to understand. So here we will take a couple of moments to define it, use scenarios to show how it can be implemented, and also to contrast it with the use of traditional physical computers. Click on and review the contents of each box to the left to learn more about these basic virtualization concepts. First, let's describe virtualization. Virtualization is a technology that allows a physical resource to be divided into a number of virtual devices that can behave like and perform the same tasks as a physical IT device. Applied to compute, virtualization is the process of dividing the physical resources of a computer, things like its memory and processor, into separate virtual computers that can perform tasks just as a physical computer does. There are some benefits to be gained from this. First, it can enhance efficiency by providing each application with resources customized to its specific needs. Resources like operating systems, CPU, and memory can be customized to the exact specifications that an application requires. In addition, as you will learn, virtualization can enhance performance and reliability by increasing manageability. We call a virtualized computer a virtual machine. A virtual machine is a computer in every way, except that it is not a physical machine. However, to the operating systems and applications they run, a virtual machine presents itself and performs tasks just as a physical computer would. Virtualization in Vblock systems involves all components, including compute, network, and storage. This is not an easy concept to grasp without using an example. So let's begin with a scenario to contrast how IT is provisioned traditionally versus how it can be provisioned virtually. The first scenario in our comparison is a traditional data center with exclusively physical computers used to host applications. The marketing department's applications may run on one physical system, the finance group's applications on a second, customer service applications on a third, and so on. Think about it. The number of physical computers and the space and other resources needed to operate them can be significant. Now understand that most applications never come close to fully utilizing the physical servers or hosts that they run on, in part because upgrades of hardware in traditional data centers is so disruptive that users often implement oversized systems. Managing data centers this way results in significant amounts of underutilized IT resources. The reality is that organizations are paying for significant amounts of IT resources that they never use. When we virtualize these applications, several applications running on their own virtual machine can run on a single physical server or host. Each runs their own unique operating system, and they are managed so that there is no interference between virtual machines operating on the same physical host. One virtual machine can freeze or crash on the physical host, and it won't affect the operation of the other virtual machines and applications running on that same physical server. It is also possible to resize virtual machines and relocate them to another physical host with little or no disruption. Running applications on dedicated physical hosts can be expensive on many levels. In our scenario, all of the marketing, finance, and customer support applications can run on their own virtual machines, all residing on a single physical host. The benefits of running virtual machines over the traditional physical servers includes more fully utilizing physical hosts and purchasing and managing fewer physical hosts. In addition, running fewer physical hosts mean not only reducing spending on the hardware and software, but it also affects spending on power, cooling, and floor space in the data center. An added benefit of virtualization is the inherent ability to move virtual machines from one host to another quickly and easily. This provides opportunities to balance the load across multiple host computers and to quickly restart a virtual machine on a new host if the host it is running on fails. There are real differences in how the resources of a physical computer are managed versus those of a physical computer running virtual machines. In a traditional physical computer, the operating system directly manages the hardware resources. Multiple applications can be loaded onto an operating system, and requests from applications to the system hardware components to perform tasks are managed by the operating system, which controls and directs the system's physical resources. In a physical computer running virtual machines, a hypervisor is used to create and manage the virtual machines. In Vblock systems, the operating systems are loaded on each virtual machine and control only the hardware that the hypervisor has assigned to that virtual machine. The operating system still directs hardware to perform tasks requested by applications, but it can only control the hardware resources that the hypervisor has assigned to the virtual machine. The role of operating systems versus hypervisors can be confusing, and some people mistakenly refer to hypervisors as an operating system. But it is important to know that they are not the same and they do different things. Traditionally, an operating system is loaded onto a physical server and applications are loaded onto the operating system. When an application needs to complete a task using a hardware component, like sending a file to storage, printing a page, or performing a calculation, the operating system provides directions to the hardware and coordinates completion of the task. In contrast, the hypervisor is software that is loaded onto a physical computer prior to the operating system and applications. It is used for creating and managing virtual machines on the server. The hypervisor securely partitions and controls a computer's physical resources to ensure that each virtual machine has and controls the resources that it needs. Once a virtual machine is created, an operating system is loaded onto the virtual machine. In effect, the hypervisor makes it appear that each operating system is running on a dedicated physical server, while in reality they are running in a virtual machine that can run alongside other virtual machines, sharing the resources of a single physical host. It is worth noting that there are also hypervisors that are loaded as applications running in operating systems. These are sometimes referred to as Type 2 hypervisors. VMware's Workstation is an example of a hypervisor that runs in an operating system. Workstation permits multiple operating systems to run on a single PC, but it has a number of limitations that it inherits from the operating system that hosts it. Because Workstation and other Type 2 hypervisors are generally not a good fit for Vblock systems, we will not discuss them further in this training. But you can click on the link or visit the VMware website to learn more about some of the other options for hosting VMs on an operating system. Remember that a virtual machine functions as a computer in every way except that it is not a physical computer. Each virtual machine thinks that it has complete control of hardware components like CPU, network card, memory, and storage drives. But in fact, what they control is a portion of the resources in the physical computer. Every virtual machine has its own operating system, which manages its virtual components. Each virtual machine can use a different operating system, such as Windows or Linux. That means that on one physical computer, multiple operating systems can be running at the same time. Also, some applications are designed to work well together on a single computer, and others prefer isolation. Just like on a physical server, multiple applications can be loaded onto a single virtual machine, or they can be installed on separate virtual machines, and each virtual machine can be sized to precisely deliver the optimum performance and efficiency. In this graphic, there are 3 virtual machines running on one physical computer, and the virtual machine in the middle has 2 applications running on the operating system of one virtual machine.
So far we've focused on compute virtualization. In this section, you will learn about the basics of storage virtualization.
Like compute virtualization, storage virtualization can provide significant functionality that minimizes system costs and simplifies the process of managing storage needs. Click on and review the contents of each box to the left to learn more about storage virtualization concepts. Storage virtualization is the process of masking the underlying complexity of physical storage resources and presenting the logical view of these resources to compute systems. Storage virtualization enables the creation of one or more logical storage components on the physical storage resources. As you learned earlier in the storage section of this training, these logical storage components are called LUNs, which appear as physical storage to the compute systems. The virtualization abstracts or hides the identity of the physical storage devices and creates a storage pool by aggregating storage drives in the storage arrays. LUNs are created from these storage pools and are assigned to compute hosts. The host system remains unaware of the mapping operation and accesses the LUNs directly as if attached to physical storage. In a block-level storage implementation, a LUN is what is presented to a host for its storage needs. A LUN is a logical abstraction of a disk drive and is conceptually a set of consecutive blocks of storage. A LUN is not a physical storage drive. It is a virtual drive abstracted from one or more physical storage drives. While it doesn't exist physically, it has all of the same characteristics of a physical storage drive. Hosts don't recognize the difference. A LUN presented to a host is viewed by that host as a physical disk. Depending on the needs of the application, a single physical storage drive can be divided up into several LUNs, all of which can be presented to a host computer as distinct storage drives. Or, if needed, a single LUN can consist of the storage capacity of several physical storage drives or parts of several drives. A host views a LUN as a distinct storage drive, even when segments of multiple drives are combined in a single LUN. The size of a LUN is configurable, with the maximum size dependent on the storage array it is abstracted on. After a LUN is created, it is presented to a host through a process referred to as provisioning. Before creating VMs to load on a host, one must create a VMware Virtual Machine File System, or VMFS. Its purpose is to store virtual machine files which contain all of the vital information required to boot and run a VM, including the operating system image and local data. Storage can be added virtually by creating a LUN within the VMFS and presenting it to the virtual machine. This LUN will reside within the virtual machine file system and can be used by the operating system as any other LUN. Some applications, such as database applications, work more efficiently with raw or unformatted LUNs. Raw LUNs can be created on storage outside of the VMFS file system structure and then presented to the virtual machine through a process similar to that used for provisioning to physical servers. When you learned about Vblock system storage earlier, we discussed thin provisioning. Thin provisioning is a method of over-allocating storage space to applications, which is a way of saying that you can promise more storage space than you actually have. For example, imagine that we have 1,000 gigabytes of storage capacity and requests from several users for a total of 1,700 gigabytes. To fulfill these requests, our storage capacity becomes over-allocated, in this example by 700 gigabytes. Normally, this does not sound like a manageable situation, but if the storage capacity currently used is only 350 gigabytes, we have sufficient storage capacity today despite being oversubscribed. Instead of granting users all of the storage capacity they have requested, thin provisioning is a process for as-needed storage allocation. When environments are new, they rarely need all of the storage capacity requested by their users. As applications' storage needs grow over time, more storage capacity can be added to support actual demand. Using thin provisioning to oversubscribe storage capacity has benefits. Cost efficiency increases when the purchase of additional storage capacity is delayed until needed. Oversubscription allows data centers to promise that the storage capacity will be there when it is needed without the overhead of maintaining unused capacity. However, when over-allocating, it is important to carefully monitor available capacity so the promise of storage space is fulfilled when it is required by the applications. Because there is a small risk of running out of space within provisioning, some organizations choose to only implement thin provisioning with applications that are not mission critical. So it is common to have a mixture of thin provisioned and thick provisioned LUNs and file systems in a Vblock. In terms of the benefits of virtual storage overall, customers achieve greater storage efficiency because storage can be customized to the specific needs of applications. Anytime a business can customize storage purchases to an application's exact specifications, they reduce unnecessary purchases, creating a positive impact on the total cost of ownership. Also, unlike the contents of physical storage drives, entire LUNs can be copied easily without significant impact to operations. This simplifies data management and protection. The ability to make point-in-time copies of LUNs and file systems makes it easier to produce backups that can be restored to a specific time in history to quickly and reliably resume operations after a problem halts processing. Without storage virtualization, system use would experience significant interruption during backup and other management tasks.
In this section, you'll learn about the basics of network virtualization.
Network virtualization involves logically segmenting or grouping physical networks into discrete logical entities called virtual networks, and making them behave as single or multiple independent networks. Network virtualization allows multiple virtual networks to share physical network resources without leaking information between them. A virtual network appears as a physical network to the nodes or devices connected to it. Network traffic within a virtual network does not propagate or appear to any node that is on the same physical network but not part of the same virtual network. This enables functional grouping of nodes with a common set of requirements into its own virtual network, regardless of the geographic location or physical network of the nodes. Network virtualization involves both virtualizing the physical network and managing the virtual networking that exists between virtual machines residing on the same host. You will learn more about this later, but for now understand that virtualizing the physical network includes virtualization of network components like network adapters, network switches, and routers. Network virtualization encompasses all of the interconnectivity of both physical and virtual resources. Within physical hosts running multiple virtual machines, there is a virtual network managed by the hypervisor and including one or more virtual switches. The virtual switches provide network connectivity between VMs and can connect to the physical network to allow communication with other devices. In a simple LAN, all of the devices connected to a switch are able to communicate and share with all of the other devices connected to the switch and also to devices connected to other switches in the LAN. This is useful but has some potential problems. The two most notable potential issues are performance and security. There are some types of network messages that are sent to every device on a LAN. These are called broadcast messages. These messages are ignored by devices that do not need to process them, but use up some of the available bandwidth of each device. The security issue comes from the fact that shared resources are usually visible to all devices on the LAN. Although security measures can make the data reasonably secure on a LAN, when malicious users are able to see a locked resource, they have an additional opportunity to attempt to overcome the security. Using multiple switches that are not connected to each other creates multiple independent local area networks. These separate LANs address the two previously mentioned problems, but at the cost of additional hardware and the power and cooling that it consumes. To address these potential issues, we can use a virtual local area network, or VLAN. The VLAN is a way to restrict network traffic to specific ports on switches. Broadcasts in a VLAN will not appear on ports associated with other VLANs, and the devices on one VLAN will not be accessible from devices on the other VLAN, even if there is no security in place to lock the resource. In a network, physical computers are connected to each other and to other network resources. The network connectivity for each computer is provided through its network interface card, or NIC. Network switches are among the other components on the network. You learned earlier that network switches manage traffic among components as data passes through the network. Virtual machines must also connect to the network. Inside the physical computer, each virtual machine has its own virtual network interface card, or VNIC. These VNICs provide connectivity to the VM and connect to the network through a virtual switch that manages traffic to the physical NICs that are part of the host. These virtual switches function like physical switches, but they are software loaded onto the physical computer. Virtual networks can be created that include both virtual and physical network resources and can span across physical computers. In this example, there are two virtual networks. Notice that VM1 and VM3 are part of VLAN A, and VM2 and VM4 are part of VLAN B. Despite the fact that they share network resources like virtual switches, NICs, and physical network switches, they are discrete virtual networks. As discrete networks, the data in each network is secure even though traffic from both networks travel over some of the same network components. In this diagram, we have been describing standard virtual switches where the virtual switch on each host is configured individually. In environments with large numbers of hosts, this manual configuration can become tedious. So vSphere also supports a distributed virtual switch, which spreads the functionality of a single virtual switch over a number of hosts. The virtual switch on all of the hosts sharing one distributed virtual switch is managed simultaneously when changes and additions are made to the configuration, such as adding a VLAN. Port channels are a way to virtualize two or more physical ports into a single logical port. The bandwidth of the ports is sometimes combined, and port channels provide alternate paths in case a physical path fails. The algorithm chosen determines how the port channel behaves in various situations, and the number of options available depends on the model of switch and network interface cards used and must be configured the same on both the switch and interface cards. A convenient way to think of a port channel is as a multi-lane highway. Vehicles can travel on each lane of the highway, and if traffic flow is interrupted on one lane, the traffic is diverted onto the other lanes. There are many reasons why companies use network virtualization. Here are a few. One important benefit is security. Despite the sharing of physical network resources, virtual networks restrict access to the devices on it and can isolate sensitive data flow to only the components on the virtual network. Network virtualization can also enhance performance by restricting physical network broadcast communications from a virtual network, which eliminates some of the network traffic and improves performance. And by enabling multiple virtual networks to share the same physical network components, it increases equipment utilization. This decreases the need for constructing separate physical networks and reduces cost.
Now, with an understanding of virtualization across compute, storage, and networking, let's discuss the Vblock system's virtualization components.
The Vblock system virtualization technology includes these components: the VMware ESXi Hypervisor and the Cisco Nexus 1000V Virtual Network Switch. We'll talk about each in turn. VMware ESXi is the industry-leading hypervisor that provides a server virtualization solution. Remember that a hypervisor abstracts CPU, memory, and storage resources so that multiple virtual machines can operate concurrently on the same physical server. It is used to create and manage virtual machines on a physical host. The physical host on which VMware ESXi software is installed is called an ESXi host. The ESXi hosts provide physical resources used to create and run virtual machines. ESXi is part of the VMware vSphere virtualization platform that is part of Vblock systems. Click on the link to access more information on vSphere. The Cisco Nexus 1000V series distributed virtual switch is designed for virtualized environments. Cisco Nexus 1000V switches are implemented in most Vblock systems. The switch has the same Cisco Inter-Network Operating System, IOS, found on many other Cisco switches, which allows customers to leverage management utilities and network administrators' familiarity with the command set for network management.
This is a learning check that provides an opportunity for you to assess your progress. Each question provides feedback to help you remember the content, and a score is provided at the end so you can assess how you are doing. This is not a test and is not part of the certification assessment. Learning check scores are not retained in your records. However, completing these learning checks is great preparation for the certification assessment that comes later. You may take this learning check as many times as you want. Click Next to get started.
Congratulations! You've completed the Introduction to Vblock Systems Virtualization. In this section, you learned about the benefits of virtualization in an IT environment, Vblock system virtualization including compute, storage, and network virtualization, and you also learned about the components of the Vblock system virtualization technology. In the next section, you will learn about Vblock system management.